Hello, in this video we're going to look at arithmetic sequences. So when we look at arithmetic sequences, we consider a sequence of which has that there is a common difference between the successive terms. In this case, notice that we have a sequence that's defined with the following terms 3, 6, 9, 12, 15, and so on. But if we look at their consecutive terms, we have that, 6 minus 3 is 3, 9 minus 6 is 3, 12 minus 9 is 3, and 15 minus 12 is 3. So in that case, we would have that this sequence in particular would have a common difference of 3. Well, in any case, for example, we can begin to define arithmetic sequence as we have that the first term would be equivalent to, let's say, some value that we just call it a, for example. But then if we start to look at, for example, like how we can define that specific sequence, well, we have that furthermore, the sequence an can be defined as an minus 1 and then plus the common difference that we call d. Now, the number a is just the first term in either case. So, like with this one, we have that was 3. So notice that if we have verified that a sequence is arithmetic, then in any case, we have that we could define the above sequence as an equals to an minus 1 plus d. In this case, though, we already know what d is. It's actually 3, so it would be an minus 1. So minus 1, and then plus 3. And notice that here that a1 was defined as 3. So if we wanted to find a2, then that would be a1 plus 3. But that's going to be 3 plus 3, which is equal to 6, and so on. Now, we can similarly, for example, define the sequence not only recursively, because in this case we have that the formula that we have written down over here, it is actually recursive. Recursive in the sense that it's going to require the previous terms in order to get the next ones and such. So we may not want to do that necessarily, so we can then think of, well, what if we were to consider, what terms would we have? So we could have the first term of the sequence, but then we could have the second term of the sequence. But the second term would be the first term plus that common difference. So we do that again, and we have a1 plus 2 times the common difference. And essentially, we're going to see that the pattern is such that we can get the sequence a sub n, and we can say that essentially it's going to be the first term, a1, plus, well, notice that here we went from the first term, so here we have our first term, then we have our second term, and then we have our third term. So it leads us to believe that essentially we have that this would be plus n minus 1 times our common difference. So now it appears that we do have an explicit formula that would define our arithmetic sequence. In any case, if we happen to know the common difference in a couple of the terms, that means that we could actually generate that said sequence. Now, suppose that we start off with a particular sequence in any case. So we'll leave that there. And we'll just say that we have the sequence of 6, 11, 16, and 21. And here we can make note that the first term is 6. Now, it wouldn't take much to verify that in fact the common difference is, the same for every successive term. So 6 or 11 minus 6 is 5, 16 minus 11 is 5, and such. So we have that the common difference in this case would have to be equal to 5. Now, it's from there kind of clear that we can actually formulate the nth term for this particular sequence. So that means that we have that an equals 2. So we have 6 plus n minus 1 multiplied by the common difference of 5. Now, what is that going to give us? It's going to give us 5n, but notice that it's going to give you minus 5 plus 6. But then furthermore, that gives you 5n plus 1. And there we have our sequence that generates those terms 6, 11, 16, 21, and such. Now note that in particular that this sequence does not converge to anything in particular. But if we were going to consider possibly like a sum of the terms, then in that case we can actually calculate that. But for a moment, appreciate that, for example, that if we wanted to find a higher order term, such as like the 100th term of this particular arithmetic sequence, that we wouldn't necessarily have to list out all of the 99 terms, but we could just plug it in as 5 times 100 plus 1, which would give us 500 plus 1, which is 501. Now, in any case, for example, if we had to go the reverse order, we could actually then figure out, like what term this would represent if we happen to know, like what is the term equal to. By that I mean, that if we had that it was 501, we would set it equal to its arithmetic sequence definition or explicit formula and solve for n in either case, of which you would end up getting that that is the 100th term. Now, in any case, the things of which that we might end up doing with a arithmetic sequence is that we might consider what would happen if we were to add up all of the terms. So this kind of leads us into this whole discussion of how if we have a sequence and we're adding it, so let's say that we have k equals 1 to n, and suppose that the sequence is a sub k. And let's say that a sub k is arithmetic. Then in that case, we would have the following. We would have that basically we're going to be adding from k equals 1 to n. But what is an arithmetic sequence in either case? Well, it's essentially the first term plus, well, here our index is k, so it's going to be k minus 1 times d, the common difference. Now, in any case, if we were going to, for example, try to get an explicit formula for this, there is a formula that we would get from this, and that would be the following. It would be n divided by 2 multiplied by 2 times the first term plus, in this case, we have that it would be n minus 1 times d. And then we just close it. Okay, because we have the open parentheses over there. But notice that if we were to separate the 2a1, that would be a1 plus n minus 1 times d, which by definition is actually equal to a1 plus an. Now, it's actually such that we could possibly look at the series sum of this and what it comes out to, because we would know that basically that we would be adding up all of the terms, for example. And if we look at what terms are those, we would see that basically that those terms are a1 plus a2 plus a3 all the way down to our nth term, so an. But consider this, that we know that every single term is going to have a common difference. Isn't that true? So we have a1 plus a1 plus the common difference d plus a1 plus the common difference for the third, so that would be 2d, plus, followed by basically a1 plus, well, here you're going to have n minus 1, so we'll probably just put some parentheses, so n minus 1, and that's going to be d. Now, in either case, what we could do is just rearrange to where we have all of the a1s grouped together. So we have a1 plus a1 plus, and basically that's going to be a1 in a set of parentheses on its own. So we have a1, and those are n terms. But essentially we would do the exact same thing with the common difference. We would have that would be basically 1, well, it would be d plus 2d plus all the way down to the nth minus 1. So we have n minus 1 times d. Now, because we have that basically this right here is n, then we can actually rewrite it one more time, to which that would be n. So we have n times a1, and we'll just write it like that. But then we have that this here has a common factor of d, so that's going to be plus d multiplied by 1 plus 2 plus all the way down to the n minus 1. Well, actually we have that specifically this is the summation of the first n minus 1 integers in either case. So in actuality, it looks like that's going to be rewritten again as n times a1 plus d times, well, it's going to be n minus 1 divided by n, multiplied by n divided by 2. So in this case, we have that we can then rewrite this. So we rewrite this in a way of which that we have that the n over 2 is going to be factored. So here we're just going to factor n divided by 2. And when we do that, we end up with n over 2 multiplied by 2a1 plus the n minus 1 times d, and then we close it. So it looks like this is the formula that we had proposed in either case, of which from there we can probably say that, well, you know, by definition, this tells us that we have n over 2 multiplied by a1 plus a1 plus n minus 1 times d. But then we have that this right here, this is just an, is it not? So then from there we have n divided by 2, and this is multiplied by a1 plus an. So now we have essentially just proven our formula, which of course, we could also prove this using induction in either case. So now it seems that we do have an explicit formula for which that can be used for adding up arithmetic sequence terms. So how we can use this? So suppose that we have a sequence of which is defined as bn is equal to, so let's say that we have 3n plus 2. Okay? And from here, let's say that we were to take this series summation from k equals 1. So let's say that we have k equals 1, and then let's say that we have 10. So in this case, we're taking 3k plus 2, and we're just going to add up all of the terms. Now notice that the terms, what are the terms? They are as follows. 5, and then we have the next term in this case, so we have 5, and then we have 8. Okay, so the next term is going to be 11. Now, of course, like we could probably continue up until the point that we find the 10th term, of which we'll get there in terms of, like what is the 10th term in either case. But we really don't need to if we have that the sequence is arithmetic, which in this case, if we check, we see that it does have a common difference of 3 in either case. And, like if you were having to start from scratch, you would just say, well, take 5 plus n minus 1, and then just multiply by 3. And then from there, we'll get the exact same formula. Okay. So how do we continue from here, though? Accordingly? Well, we know that basically that it has to be that we will take basically the n divided by 2 multiplied by the first term, which in this case is 5, but then plus the nth term. But in a way, we kind of already figured out like what the nth term would actually happen to be. So in this case, that would be 3n plus 2, of which from here you can say that that's 3n plus 7 if you want to do it like that. So you have n divided by 2, and then that would be 3n plus 7. So in this case, we have that the solution for this would be determine that n is 10. So here we can actually just replace the n with 10. So here we can replace the n with 10 because, we have that there is a nice formula that says that we can just replace it. So we have the 10 divided by 2, which in this case is 5, multiplied by 37, which when we get this gives us 185. So we get that the solution, if we were going to add from 5 to 32, it would be such that the solution would be 185, but we didn't really need to do that. Now, if, for example, that you actually recognized that you can take the summation symbol and distribute it over the addition, you would be correct because we have that essentially the properties of sequences allow us to do that, where we take the 3 and then we would have the sum of k equals 1 to 10, and then we would take k and then plus the series summation from k equals 1 to 10 of 2. But using basically the formulas that we look at in this particular section and previously, we have that would be 3 times 10 times 11, but then this would be divided by 2, and then we have that this would be plus 2 multiplied by 10. So from that point on, we could probably work it out to where we have that this would be, let's see, so here we have that this would be 30 and that would be 15. So we have 15 times 11 plus 2 times 10. And, like if we were going to take 15 times 11, that would give us 165. I just needed to double check. So we have 165 plus 20, of which gives us the exact same thing of 185. So, if we were to recognize that it was an arithmetic sequence or not, we would essentially get the exact same thing either way. Now, if, in any case, like we had certain sequences of which that we knew were arithmetic, we can actually derive formulas from the statement of an arithmetic sequence. Now, giving you kind of like an example of like when that would occur, it would be such that, for example, that if I had considered, for example, the odd numbers. So like if I had considered an odd number sequence, such as 2n minus 1, I can actually derive a formula such that if I was going to add from k equals 1 to n, and my sequence is defined as 2k minus 1, I can actually verify that the sequence, and when we add from 1 to n for this, is going to be equal to, well, here we take n, we divide by 2. What do we take? We take the first term. The first term of an odd number sequence would have to be 1. But then we add it to the nth term, which in this case would be 2n minus 1. But then notice that the 2n will be added to 1, but subtract 1, or, 1 minus 1, that cancels out. But then we see that basically you end up with n over 2 multiplied by 2n, and that gives you n squared. So essentially, we have basically a formula that defines what happens if we were to add from k equals 1 to n for a odd number sequence, so 2k minus 1, and we propose the solution to be, or the formula to be n squared. And then, from there, it's just a matter of, like if we were going to add the first 11 odd integers, then in that case, it would just be 11 squared, which is 121. Now, you could probably look at, for example, what happens if you look at even numbers, knowing that their common difference is always going to be 2. And if you looked at their summation, you would basically find that it's very similar to this one, but it's going to be a little different because it's going to be n times n plus 1. So I can leave that as an exercise where you try to find, like, if you have the even sequence and you have that you're just adding from k equals 1 to n, and that's going to be 2k, what would be the formula for this one? Okay.